Hello, welcome to lesson 4 of chapter 6, Trigonometric Functions. Today we're going to prove and apply the identities that we've met already. Sec squared theta is 1 plus tan squared, which we derived from the diagram. And the second Pythagorean identity, which we uncovered, was cosec squared is identical to 1 plus cot squared. As usual, there's the GCSE to A-level transition booklet prerequisites and some of the work from last year. There's quite a lot there, algebraic expressions, quadratics, algebraic methods, and a lot of trig as well, because we're going to be, as we progress through the course, we're going to be fusing together lots of different topics. Okay, so at this point, please pause the video, have a go at the 4 warm-up questions, and I will go through the answers. Great, okay, let's have a look at the solution to question 1. So for question 1, we're asked to tick the quadrants where sec theta is positive, and we've got the cast diagram there. So just to recap what sec actually is, if we use that third letter rule, okay, well, the third letter rule wouldn't apply here. It's the first letter rule, really, isn't it? Because we've got the new, I'll put new in inverted commas, the new trig ratio, sec. So if we just remind ourselves what sec theta is identical to, that should make things a little bit more obvious. So I'll just write it out here. So sec theta is identical to 1 over, just rewrite that, wasn't very happy with 1 over cos theta. And the rule I was just alluding to was, of course, this third letter rule. So the third letter of sec c is a reminder that it's the cosine reciprocal. Okay, so we know that. So now we know sec is 1 over cos theta. If sec is negative, then so will 1 over cos theta. That will also be negative. If sec is positive, then so will 1 over cos theta. So we just have to look for where cosine is positive. Okay, so cosine will be positive in C and A. All right, but we're asked to put a tick, weren't we? So we'll put a tick there. So this is also where sec is positive, okay, because it corresponds to the reciprocal of cosine. So it's quite a simple introduction there. Moving on to question 2, the first thing we have to do is find the length of the hypotenuse of this right angle triangle. Now, this is a classic Pythagorean triple that we've got here. It's one of those things you probably know already. So we've got a 3, 4, and as is always the case, the hypotenuse must be 5. It's what we call a 3, 4, 5 triangle, or the 3, 4, 5 Pythagorean triple. If you're not convinced by that, or if you didn't know that, you would obviously have to use Pythagoras' theorem. So you would simply just say, okay, 3 squared plus 4 squared, which would give you 25, and then you would very quickly see that the square root of 25 would be 5. Okay, so we've established that, and once we know this, we're asked to do something with it in part B. So it says, given that tan theta is 3 over 4, well, they've given us that, but we can see that from the diagram that tan theta is, of course, 3 over 4. And we know theta is acute because it's a right angle triangle. So we have to find some exact values. Well, let's just make a list of all the information we can see from this triangle. I think that would be a good idea. So the first thing to notice is we know, well, we've got tan theta, so we also know what sine theta is. Okay, so sine theta is, of course, the opposite over the hypotenuse there. So put those on. So that's going to be 3/5. Okay, we can also determine what cos theta is. So cos theta is going to be the adjacent side over the hypotenuse. So that's going to be 4 over 5. Okay, tan is given to us in the question, but this also unfolds lots more information because we've learnt some new trig ratios, haven't we? Okay, so we also know some more things, which I'm going to list on the right hand side because I'm running out of space. If we use that third letter rule, okay, for our old trig ratios, we've got sine and cosine there. They correspond to the third letters of our new ratio. So we can say something about cosec and sec. So we can now see that cosec theta must be equal to 1 over sine theta, so that must be 5 over 3. Okay, and we also know that sec theta must be equal to 5 over 4, just a reciprocal of 4/5. And the one thing we haven't mentioned is the tan theta here. We can reciprocate that, and that is, of course, cot theta. So I'm going to make a note of that, cot theta, which is going to be 4 over 3. Right, so loads of information in that right angle triangle. And we've also managed to identify the first answer, B part I. So we know that cot theta is, of course, 4 over 3. Now, for sec squared theta, we can just take the value of sec theta and square it, which is essentially what sec squared means, isn't it? Let's fill that in. So sec squared theta, not much space there, I apologize. So we just take the 5 over 4, which was sec, and we square it. I'll do here. So that would be 25 over 16. Now then, this would be a nice opportunity just to test one of those identities. So if you remember from the lesson objective and from what we found earlier, sec squared is identical to 1 plus tan squared. So the question is this the same if I put in 1 plus tan squared? Well, let's do that. Now the tan value, which was given to us in the question, which is quite nice, isn't it? Because that means I could, if I didn't have any other information, without going all around the houses and finding out this summary of information from the triangle, I could just use whatever's presented in the question directly, couldn't I? So I could just put in the tan squared theta, add 1, and then I get the sec squared theta immediately. Okay, so let's check that. So if we put that in, that's going to be 1 added to 3 over 4 squared, which is essentially going to be 1 added to 9 over 16. And we're going to add these fractions together. Now, I've got one whole one there. I'm talking about 16s here. So that's going to be 16 over 16 added to 9 over 16, which does indeed give the 25 over 16, which we already knew, but it's just nice to verify that, isn't it? So it definitely works in that instance. Now for part 3, cosec of pi over 2 subtract theta. Well, this looks complicated, but if we go back to the diagram, we know quite a bit about this angle pi over 2 subtract theta, and we'll look at a different technique. Well, there's many different techniques really, but there'll be new techniques to evaluate this later in the course. But this angle here would correspond to the unlabeled angle up here. If I just do some simple angle reasoning in this triangle, you'll see very quickly that because it's a right angle triangle, pi over 2 corresponds to 90 degrees. So this angle here would be pi over 2 subtract theta, okay, which indeed is the angle we're talking about here. So I have to find the cosec of this angle. Well, cosec, of course, is 1 over sine, so we'll just make a note. So we know for part 3, this is the same as 1 over the sine of pi over 2 subtract theta. Just extend that a little bit. Now then, So we have to find the sine of this angle here. Okay, so remember, sine is the opposite over the hypotenuse, which I've just ticked. So this must be equal to 1 over the opposite over the hypotenuse, which would be 1 over 4/5. Okay, and the reciprocal of 4/5 is, of course, 5 over 4. And have we already seen that? Well, yes, this corresponds to sec theta, doesn't it? So that's rather interesting. So we've seen that the cosec of this angle, pi over 2 subtract theta, is the same as the sec of theta. Okay, so there's that, and you'll remember this perhaps from when we sketched the graphs. They are translations of each other, aren't they, by 90 degrees or pi over 2 radians. Okay, so that's the first two questions. Now for question 3, you'll probably find it easier just to draw that right angle triangle again. Now, it might sound counterintuitive because we're told in the question that theta is an obtuse angle. It states it here very clearly. Now, what I would recommend is we're going to pretend that theta is acute first of all, and then we can see the ramifications of that by transferring that information to theta being obtuse. So you'll see what I mean. If we just draw the triangle that was given to us in the previous question, there's a bit of scaffolding. If I just draw this again, so we've got, we'll put theta there, okay, and we'll label the sides. So it's, we know that tan theta, just ignore the fact that it's negative, okay, that's not going to happen. Just pretend it's an acute angle. So we've got a 3, 4, 5 again. So 3, 4, and 5. And we'll just make a note of everything we know, and we'll just state, just for clarity, that, so we're just going to assume initially that theta is acute. Spelled that wrong. Okay, just enables us to visualize it first if we do that. So now we can answer questions 1, 2, 3, and 4 fairly easily just by writing down the information. So sine theta opposite over hypotenuse, that's going to be 3 over 5. I know we've already done this, but we're going to compare in a second. Cos theta is adjacent over hypotenuse, that's 4 over 5. Okay, and then remember the first letters of these correspond to the third letters of our new trig identities. So we've got cosec and sec in that order. So we're going, we also know that cosec of theta is, of course, 1 over sine. So that's going to be a reciprocal of 3/5, which is 5/3. And sec theta is going to be 5 over 4. And we already had that information from question 2. So there's no need to recycle that. I'm just doing this for clarity. Now we can assume that we can extend this and say, what about theta when it's obtuse, which is what's required here. Okay, so I'll just put a partition there. Now, to transfer this information to an obtuse angle, we use the cast diagram. So I'm going to draw a cast diagram for this. So I'll put that here. So CAST, like that. And now we can assume that theta is obtuse. So now assume theta is obtuse, and we can add it to the cast diagram, which I'll do now. So theta, it would start here, and it's greater than 90, but less than 180. So that would be my angle theta. And that means, of course, that if it's obtuse, it lands in the sine quadrant, where sine is positive only. Okay? So remember, that's what that means. Sine is positive in this quadrant, but nothing else. Now, I've just answered the question for you now. So these values that we met in the previous question, all the stuff we worked out here is still valid, okay? They're still the same values. It's just a case of what sign are they, okay? That's the only thing that changes when we navigate around the cast diagram. So we transfer between acute, obtuse, and reflex angles, okay? So we can answer this really easily now. If it's got anything to do with sign, it remains positive. If not, we just change it to a negative value. So therefore, so we can answer the question now. For part 1, sine of theta remains positive. So it's going to be 3/5. Okay. For part 2, the cosine. Now, notice the cosine is going to be negative in that quadrant, so we have to change that to negative 4/5. For part 3, now cosec, remember, is 1/sine, the reciprocal of sine. So that means the cosec is going to be positive as well. So I reciprocate sine, I get 5/3. And lastly, the sec value is 1/cos. So I reciprocate what I've just found for cosine, so that's going to be negative 5/4. And that's all you have to do. So I think just to get the values, and irrespective of what sign they are, to get the values first, pretend your angle is acute, and then you can use cast to allocate the correct sign to it. And it doesn't matter which quadrant it falls in, the question will tell you this, and you just allocate the signs accordingly. Okay, now moving on to question 4, we have some factorization to do. If we look at A, first of all, let's look for some common factors in those terms. Well, it looks like we've got an x that will appear in both of these, so I can definitely factor out an x. So let's do that first. There's always a hint here when it says factorize fully. You know there's probably going to be more than one step here. All right, so factorize fully. So I bring the x out. So this is for part A, of course. Now let's see what's left. So we're going to have x squared, subtract, and y squared. Okay. Now, you might get some credit for that, but you won't have answered the question, because we can hopefully see clearly now we've got the classic difference of two squares situation here. So usually an early question on the old C1 paper or the AS paper for pure. So we need to factorize this using difference of two squares. So we would have x add y, x subtract y, in either order, it doesn't matter, and then we've got that fully factorized. Now for part B, which I'll do underneath, so I've got a bit more space. So this was for part A. For part B, now if you notice, we've got x to the power 4 subtract y to the power 4. We could think of this again as difference of two squares, and what I mean is we've got x squared, okay, that's x to the power 4, subtract y squared, but that's also squared. Okay, so it's a difference of two squares now. So now I can write that as a difference of two squares factorized. So the next step would be, okay, well, my two elements squared, I have to add them and subtract them in two separate brackets. So we're going to have x squared add y squared for the first bracket, multiplied by x squared subtract y squared for the second bracket. Now, again, we've only used one step. It's probably going to be a bit more to it. Well, we've already factorized x squared subtract y squared, haven't we? That came up in the previous question. Okay, so we know we can factorize further here. For the other one, this, we can't do anything with this. It's not the difference of two squares, it's the sum of two squares. Nothing else we can do with that. So we just have to rewrite the right-hand side as 2 brackets. So let's do that now, and then we can finish this off. So it's going to be x squared add y squared. Okay, and then we're going to have x plus y, x subtract y. Okay, so you might be wondering why we're going back to something that you probably did right at the beginning of year 1. Well, it's going to rear its ugly head again in this lesson. Okay, so that concludes the warm-up. Now, before we get into the worked examples for this, the 2 main identities that are the focus of this lesson that we actually derive from the diagram, the unit circle, earlier in this chapter. We're going to have another look at deriving these identities. Now, this is a useful exercise for you guys to do, and they are technically valid exam questions in their own right as well. So not only is it you could actually gain some credit from this, if you forget these identities, which are not provided for you in the formula booklet, this could be a good way to quickly sort of refresh your memory. Now, I'll just show you how to do these really quickly, and then I would recommend every now and again perhaps doing this on a flashcard and maybe just practicing sporadically while you're doing your other work, just to make sure that they stay at the forefront of your mind. So we're going to have a look at sec squared theta is identical to 1 plus tan squared theta. So how can we get this result if we don't remember it, or we can't remember it and we want to get it quickly? How are we going to find this out? Well, there's one way to do it which is quite nice. If we take the identity from last year, which I'm sure you all know by now, all you need to remember is this identity. Okay, so we'll take sine squared add cos squared is identical to 1, and we're talking about theta in this instance. So write down the identity from last year. Sine squared theta plus cos squared theta is identical to 1. And then if we just have a look at the identity that we're trying to derive, there's a couple of things to notice about this. There's hidden clues. Well, if you know how to look for them. Notice we've got tan squared in this. Now, there's another identity that you were familiar with last year, and that was the tan theta identity. So we also know that tan theta is identical to sine theta over cos theta. Okay, so we're kind of minimizing the amount we need to remember for this. How would we generate tan squared theta? Well, we'd need to have a sine squared theta over a cos squared theta. Well, if we look at the identity I've just written out, it's sine squared plus cos squared in there. If I want to generate a sine squared divided by a cos squared, which echoes the tan squared, all I need to do is divide the whole thing by cos squared. Okay, so that's what I'm going to do. So this is the first step. We're going to divide every single term by cos squared theta. Okay, now this is valid. If you do it to every single term, this is still the same identity. Okay, so that's the first step. Now, the result will just fall out now. So if we see that sine squared over cos squared, we've already mentioned this is tan squared. So we have tan squared theta. Okay, and then we have cos squared over itself, which just simplifies to 1. And then we have 1 over cos squared. So remember the third letter rule of the new trig functions corresponds to the first letter of our original trig function, which was c. So this must be sec squared. Okay. And there we have the identity. I mean, it's not written in the same order, but it's the same identity nonetheless. Okay, so that's how we could do it quickly. So you simply take the identity from last year that you know well, you've used regularly, and divide all the terms by cos squared, and you get the sec squared identity. If we move over to the cosec squared identity, you'll probably be on the same page as me now and think, okay, it's going to be a similar idea. So if we write down the sine squared plus cos squared identity first, like so, and we have a cot squared in there. Now, if we divide the whole thing by sine squared this time, okay, this would give us the cos over sine, which corresponds to cot. So I'll just make a note of that as well. So we know that cot theta, remember, is the reciprocal of tan theta. So it's going to be cos theta over sine theta. And because we have sine theta in the denominator here, we want to generate sine thetas in the denominator on this, in the same way as we had cos theta in the denominator there, and we created cos in the denominator all the way across. So this time we're going to divide everything by sine theta. Let's do that. Sine squared theta, I should say. So sine squared theta, and sine squared theta again. Okay, and now we just have to hopefully remember what each of these represents. The sine squared over itself is, of course, just 1. Cos over sine, we've just indicated that's going to be cot squared. Okay, and 1 over sine squared, well, again, use that third letter rule from these new trig functions. So S, so it's the one with S as the third letter, which of course is the cosec, which we can see right in front of us. So that's cosec squared. And there you have it. So you've got the identities, and they just fall out of the one identity that, well, 2 perhaps that you had to learn last year. Okay, so you don't have to remember these new identities, but I would strongly recommend you learn them anyway, because having them in your toolkit is really important. Okay, and it just makes you a much more efficient mathematician. Okay, so worked example 1, we're given some information here about tan x, and we're told that it's a reflex angle. Now, it's a particular type of reflex angle. Obviously, reflex encompasses all angles between 180 and 360. So this is the information. Now, this would be what I would call a quadrant 3 reflex, so between 180 and 270. So that would be in the tan section of the cast diagram, but we'll get onto that later. With this information, we're asked to find the exact values of sec x and cos x. We've actually touched on this already in the starter, okay, the warm-up, as I should say. What I recommend we do is we're going to do some sort of derivation of what sine and cos of x might be, but we'll assume that x is an acute angle first. Okay, so before we address the question head on with this reflex angle x, let's look at the acute version. So first of all, let x be an acute angle. Okay, and that way we can use a right angle triangle. So I'm going to draw a right angle triangle now. Okay, we'll put the angle x here. Doesn't matter where you put it. And we can now label the triangle because we've got this information presented to us rather conveniently. We've got the 7 there. So that's, if it's tan, that's the opposite side, of course. So this is the opposite. And this must be the adjacent. Okay, so we put that on there. That's going to be 7 for the opposite side. Adjacent side is 24. Okay, and to get the hypotenuse, which we'll need to get the sine and the cosine of x, we just need to do a little bit of Pythagoras. If you don't recognize this as a triple, a little bit of Pythagoras will do the trick. So hypotenuse squared is going to equal 24 squared added to 7 squared. If you do that, you'll discover quickly that this is 625. So therefore, the hypotenuse must be the square root of that, which is 25. So this is a triple, okay, if you didn't recognize it. So let's label that on there. So this is 25, just from doing a bit of Pythagoras' theorem. Okay, so we're ready to write down some information. Now, we need to find sec for part A. Obviously, sec, if we use that third letter rule here, that's going to be the reciprocal of cos. Okay, so if we write down what cos is, we should be in business. So from the diagram, we can see that cos x is going to equal the adjacent over the hypotenuse. That's going to be 24 over 25, like that. And we can also, for part A, they seem to be the opposite way around parts A and B, but never mind. For the other part, we reciprocate that, so we know that sec x is going to be the reciprocal of that, which is 25 over 24. Okay, and we could find sine x and cosec x just as easily. Okay, so that's with x as an acute angle. So now let's move over to the answering the question. So for x as an angle between 180 degrees and 270, we're going to use cast. Right, so let's draw a cast diagram now. So, okay, just label that. They've been very useful, these diagrams, over the last year or so. And we establish which quadrant we're interested in. Well, 180 and 270, as I said earlier, was quadrant 3, which I would call the tan quadrant. So it's where tan is positive, of course. Now then, if we put the angle in there, the x angle is a reflex angle in here. Okay, so everything apart from, let me say that again, only tan is positive and all the other angles will be negative. So we can now answer the question. So this means that for part A, the sec angle, because sec is 1 over cos, this is going to be negative in this quadrant. So it's going to be negative 25 over 24, which we found on the left-hand side of the screen. And for part B, cos x, which we actually got first, would be negative as well. So that'd be negative 24 over 25. Now, if you just wanted to check this on a calculator, what we can do is if I just select option 1 on the calculator here, what we were aiming to do was to obviously find the tan of the angle x. Okay, so it was 7 over 24. If I just inverse tan, now my calculator's set to degrees, so there's no problem there. That was 7 over 24. Now, if I do that, remember, this is the principal angle, essentially. So it's going to give me an acute angle, 16.3, roughly. Now, the angle we're interested in, of course, is as a reflex angle, and it makes the angle 16.3 with the horizontal. So I need to add 180 degrees to that to get the angle we're interested in. So 196.3 is the angle X in this situation, which we're not asked to find, but it's there anyway. Now, if I, just to verify, let's say part B, which I can do on the calculator, if I take the cosine of that angle, which I'll do now. So the cosine of that angle, so if I just press cos and then just answer, so that will be the 196.3, but it will be exact on here, and press equals, you can see I get the negative 24/25. Okay, and then the sec would be the reciprocal of that, which is also negative. So I think that sort of proves that we seem to be on the right track here. Okay, for worked example 2, we have another reflex angle, theta in this case, and it's in quadrant 4 in this situation, between 270 and 360. So that's the cosine quadrant where cos is positive. And we've given some different information this time. We're given some information about cosec. All right, so once again, what I recommend we do is we assume that theta is acute first of all, and then we can get the values, and then later we can assign the positive or negative sign accordingly. So the first thing to do is, let's just say, assume theta is acute, or let theta be acute, whatever, however you want. Now we can talk about right angle triangle. So let's draw the right angle triangle as well. Just good for reference. Put the angle theta on there. Okay. Now we can assign some values to the triangle. We're given cosec in the question. Now cosec, of course, from that third letter rule, you're getting familiar with it now, as letter S as the third letter, so we know it's the reciprocal of sine. So we know that 1 over sine theta is equal to 17 over 8. We'll dispense with the negative because we're talking about acute angles now, and sine, cos, and tan are all positive for the acute angles. So this means that sine theta is going to be 8 over 17. Okay, so this is sine theta. Okay, so we need to make sure we assign the sides correctly. So this is, of course, the opposite, and this is the hypotenuse. So let's add those to the diagram. So the opposite side is 8, and the hypotenuse is 17. Okay, now again, if you're not familiar with your Pythagorean triples, okay, we can just use the calculator. I'll use the calculator in this instance. So we need to find out the short side. So if we do 17 squared, subtract 8 squared, we get 225. Take the square root of your answer, and of course that's 15. So from a bit of Pythagoras' theorem, we've got all three sides pretty quickly. So this is 15. Okay. Now, what do we need to find? Well, later on, we're going to be asked to find cot and tan. So let's write down tan and cot in that order for these acute angles. So we can see from the diagram, now we're not answering the question, of course. These are for acute thetas. So we can see that tan theta is the opposite of the adjacent, so 8 over 15. So that's done. And to get cot, we reciprocate that. So therefore, cot theta is going to be 15 over 8. Okay, and we've got the values. Now, we just have to decide what sign the values are going to be, so we can answer the question fully. So on the right-hand side of the page, just get rid of the calculator. So we've got a bit of space. So we're going to use cast again. Sorry, so for theta between 270 degrees and 360 degrees, we're going to use cast. So get your cast diagram. And just make sure you get the right quadrant. So let's see how far around we need to go for this. So starting at 0, between 270 and 360, the angle is somewhere in this quadrant here, which is of course the cosine quadrant. We'll use a bright green for that one. Okay, so only cosine is positive in that quadrant. So that's very useful. Now we can answer the question. So going back to what we're asked to do for part A is to state what cot theta is. Well, cot theta we got earlier is 15/8. Remember, cot is the reciprocal of tan. Tan is negative in this quadrant. So we know with a good deal of certainty that cot theta is going to be negative. So that's going to be negative 15/8. And for part B, we just write it down. Tan theta will also be negative. So that's going to be negative 8/15, the reciprocal. Okay, and I think we're done with that one. Now then, for worked example 3, we're asked to do a proof, and this is going to be the first of a series of proofs. Okay, so we take a left-hand side of an identity or a right-hand side, and we show that the opposite side is, of course, the case. All right, so at no point are we showing both sides of the identity at any stage during this proof. What might be useful, if you don't have them in front of you, is just to write down the identities that we've seen already today, which is the focus of the lesson. So we need to be familiar with the sec squared identity, and I'll write it in the same context as the question. So the angle is called A. So we know that sec squared A is of course 1 plus tan squared A. True for all values of A. That's what an identity is. We also see the cosec identity featured here. Just reading from left to right. So cosec squared A, and this came up again, you can derive these yourself, is the same as 1 added to cot squared A. All right. Now, notice that on the right-hand side, the tan squared and the cot squared are both present in the identities I've already written here and here. So everything seems to be accounted for with these two identities. Now, I'm going to start with the left-hand side here. Okay, and we're going to show that the right-hand side is indeed the case. So we're going to substitute straight away. So I can see that if you have one eye on where you want to be, you want everything on the left-hand side to be transferred or substituted for terms of tan squared and cot squared. And these identities will allow us to do that. So you can see straight away that the sec squared that I've got here, I can replace that with 1 plus tan squared. So I'm going to do that first. So we're going to have 1 plus tan. So on the left-hand side, we're going to have 1 plus tan squared A, which is replacing this. Okay. And just to make it really clear, I'll put this in brackets. Okay. So I've substituted sec squared for everything inside that bracket. And then I'm going to be subtracting cosec squared. Now, brackets are really important here as well. Now, cosec squared, as we can see, I can replace this with 1 plus cot squared. Okay, so I'm going to do that. So that's going to be 1 plus cot squared A. And I'm going to close that bracket as well. Okay, I'm not putting that identical to anything. Okay, I'm just going to show that we're going to get tan squared subtract cot squared later. So this I can now expand the bracket if you like. I've got a negative in front of a bracket, which means that second bracket is being multiplied by -1. All right, so the first bracket is just dispense with those brackets now. Don't need them. Now I'm going to have a -1, and I'm going to be subtracting the cot squared as well. All right, so is there any, or are there any terms we can collect? Well, the ones, if you see, we're going to have some cancellation here. We've got a +1 there and a -1 there. That immediately cancels. And I think we're in good shape now to write down the final answer. So this is just identical to tan squared A subtract cot squared A as required. Okay, so a nice introduction to proof. So just go down through the steps, identical to in each step, but don't at any stage write both sides of the identity down. Focus on one and show that it is indeed the same as the other side. Now for the example 4, we have another proof, and just to get us started, I've just written out the identity that looks to be the most useful in this situation. If we just scan across what we've got here, everything is in terms of sec and tan. Okay, so that means I can use, or I'm thinking about using this identity because I'm going to be interchanging between sec and tan probably quite regularly here. The other thing you need to be aware of is the added complexity, which excuse me, getting tongue-tied again, with which these identities can manifest. Okay, now what I mean is you can call these angles whatever you want. So in this instance, we've got 3 theta's everywhere. It doesn't matter. Okay, as long as the identity matches that, as long as you swap 3 theta on the left hand side for 3 theta on the right hand side in this, then you're being consistent. Okay, so it's just to make it look more complex. Okay, but it's not. Okay, the angle, you can call it whatever you like, doesn't matter. Now let's see how we can approach this. Well, we've got power 4s on the left hand side, which is a little bit worrying. So let's start with the left hand side, because clearly those power 4s make it the most complicated. Let's see what we can do. Well, if you cast your mind back to warm-up question 4, we had a situation where we had something like this. Okay, and we can recognize this as a difference of 2 squares, and we saw that we can factorize this quite easily into 2 brackets, such as x squared subtract y squared, or add y squared, and then x squared subtract y squared, using that idea. Now this is a powerful idea, because if you notice, it drops the powers down in each of those terms by 2. We don't have identities for power 4. We only have identities for power 2, but I can get straight to those power 2 identities with a nice factorization. So you can see in this instance, if I say, okay, if x is sec 3 theta and y is tan 3 theta, we can simply factorize the whole thing. All right, so let's have a go at this. So on the left-hand side, we've got a factorization. So let's start with a bracket. And we're going to have sec squared 3 theta added to tan squared 3 theta. Okay, that's using the above as a model for this. So what I mean is referring to this bracket here. Okay, so again, you could think of the x is equal to sec 3 theta. Okay, you're not making a substitution necessarily, it's just a way of thinking about it, and the y would equal the tan 3 theta. Okay, and for the second bracket, we would have the same again, but with a negative sign. So we would have sec squared 3 theta subtract tan squared 3 theta. Right. I would just sort of step back and just soak that up for a minute and just make sure you're happy with that step. Okay, that's the most important step and perhaps the hardest step of the proof. Okay, but you can see now we're only dealing with sec squareds and tan squareds. Okay, and I'm being consistent across the board here and making sure we're putting 3 theta in all the way across. Okay, that's the name of the angle. That's what it's been assigned, so we have to use it. Now, the next step is, if we look at the right-hand side of my identity, the thing I'm aiming for, always having one eye on this, everything is in terms of sec, okay? So what I need to be thinking is, how do I eliminate the tan squared here and the tan squared here? Can I get this in terms of sec? And yes, I can. That's what the identity is for. So the identity that we wrote down right at the start, or I wrote down in advance here, is the key. So the next step is we're going to put our identity sign on there, okay, and we're going to make the substitutions inside the brackets. So we have got sec squared 3 theta added to, and we'll make the substitution now. So that's going to be, well, sec squared. Now I've got tan squared 3 theta. What I need to do is do a little bit of manipulation. So if I take this identity, and if I subtract 1 from both sides, you can see we can get tan squared isolated on its own on the right. So that means that tan squared is identical to sec squared subtract 1. So that's what needs to go in here. So sec squared 3 theta subtract 1. Okay, these proofs, there's no sort of set way of doing them. It's just a case of, you've got a toolkit, you know, with the identities and like the difference of 2 squares in this instance. You're just using all your skills, okay? And it's a problem solving exercise. All right, so I can't give you a formula for each one of these. It's just a case of you using your own intuition. On the right hand bracket here, we've got sec squared 3 theta. Okay, and I'm going to be subtracting. Now I've got to be careful here because I've got a negative. So I'm going to use parentheses again. So this is going to be sec squared 3 theta subtract 1, which is replacing my tan squared 3 theta. Right, so this is looking complex, but we should be able to collect some like terms now. Now then, inside the first bracket, what have we got? Well, we've got sec squared 3 theta twice. I can collect those together. So that's good. So inside this bracket, I'm going to have 2 lots of sec squared 3 theta, 2 of those objects, subtract 1 on the end. And in the second bracket, I'm just going to put an extra step in here because I've got a negative sign, which is going to cause some problems. So I've got the sec squared 3 theta that I had originally. I've got a negative outside the bracket, so I'm going to be subtracting. Do this in red, make it emphasize, subtracting sec squared 3 theta. And if you'll notice, we're going to have the double negative here and here, so that's going to be +1. Really important we get that right. Okay, so we've got some tidying up to do in the left-hand bracket. Sorry, I beg your pardon, the right-hand bracket now. So we've got 2 sec squared 3 theta, subtract 1. And if you'll notice, the sec squared 3 thetas are going to cancel. So all we're left with in that right-hand bracket is just 1. And you'll notice this is exactly what we wanted. Okay, so we've got our answer. So I can just write down the answer now. And this is what may be off-putting as well. You may see some really, really complicated looking steps and think this isn't going to simplify. And then an identity might pop out that you can use, or something will cancel, and then it will all come good in the end. So just have faith in your own skills here. So if I just write down the final step, which is the right-hand side, and I think we're done there. So example 5, we have an expression that we have to verify as r squared in part B. And then we also have to express q in terms of p for part A. Now, we've been given a few pieces of information here, so we would expect to use all this. So we're told that p is equal to, notice it's not identical to, but it's equal to cosec theta, okay? Q is equal to sine theta, okay? And r is equal to sec theta. Right, so we've got 3 pieces of information. So if we start with P, in part A, we're told to express Q in terms of P. So we just write down these 2 as a starting point, and let's see what we can do with it. So we're told P is equal to 2 cosec theta, and Q is equal to sine theta. Now, what is the logical thing to do? Well, is there a link between P and Q? Well, the answer is, of course, yes. If we use that 3-letter rule again, cosec is, of course, 1 over sine. So that means I can rewrite P as follows. So therefore, P is just going to be equal to 2 over sine theta, okay, from some information we already had. Now then, we also know that's given to us that Q is equal to sine theta here. So I can just do a straight substitution now. So it was actually very simple. We can just simply state that P is going to be 2 over Q. All right, and now we have expressed P in terms of Q. Now, that's good. We've got the sort of reverse of what we wanted, but it doesn't say express Q in terms of P. So the Q comes first. So that means we need to make Q the subject. So let's just make a note of that. So now make Q the subject, because it says express Q in terms of P, not the other way around. So therefore, if we just swap them around, Q is going to equal 2 over P. All right, so that would be part A. Now for part B, we have a show that. Now there's a few things to consider here. Now we have, once again, it's not an identity, but we have a rather complex looking right-hand side in this equation, okay, or this formula. So maybe if we start with the right-hand side, and if we can show that's equal to r squared, that would be really good. So if we just put a summary of some information that we already know. So we know that r is equal to sec theta. We've not used that yet. Okay, so therefore r squared is equal to sec squared theta. Okay, and we've also got p squared in this. We've got p, we've dealt with p already. P is equal to 2 cosec theta. So therefore p squared would be the square of that. Now if we square p, we've got to square the whole thing. Now I'm just going to put this in 2 steps to make this absolutely clear and we don't make a mistake. So it's 2 cosec theta all squared. Okay, and that's going to be, so if I square the two, remember I'm going to get 4 cosec squared theta like that. Right, so can we apply this information? So I'm going to start with the right-hand side, and hopefully we can do some simplification, perhaps some collecting like terms, and we're going to end up with hopefully sec squared theta, which is of course r squared. So let's write everything out. So if we start with the right-hand side, I know it's not an identity, but it's a show that. So let's start with the right-hand side. We've got p squared in the numerator. So we've got 4 cosec squared theta in the numerator over the same thing. So that's going to be 4 cosec squared theta. Okay, that's my p squared, and then I've got to subtract 4. Okay. Now then, what can we do with this? Well, I can do a factorization in the denominator. If you notice, we've got 4 in both terms here. So I can factorize the 4 out, and let's do that. Let's see what happens. So this is going to be equal to 4 cosec squared theta in the numerator over, and I'm going to take the 4 out at the front. Okay, and then if I factorize that, we're going to be left with cosec squared theta subtract 1 if I factorize that. Okay, so I can cancel the 4s now, so that's good. That means that we have cancellation here and here, so they're going to just simplify to 1. So I've essentially got cosec squared over cosec squared subtract 1. Now, we've got one eye on what we want to achieve. We want to get to this sec squared theta. Okay, now I can simplify the cosec squared subtract 1 using one of the identities, which is the basis of this lesson. So remember, of course, so I'll put a little note here that cosec squared theta is identical to 1 plus cot squared theta. So therefore, with a bit of rearranging, if I subtract 1 from both sides, I get cot squared theta, but I also get the cosec squared subtract 1, which is exactly what I have in the denominator here. So I can replace, so I just do that step just on the side there so we can see the simplification. So we're going to get cosec squared theta over cot squared theta. Right now, at the moment, that looks quite complex. This is supposed to be sec squared theta. Now, what a good idea, and we saw this in a previous lesson with proofs of this sort, or it's a show that. I know it's a show that, but it's a similar idea. A good thing to do is to write these reciprocal functions as their basic building blocks. Okay, the basic building blocks of all these functions is sine and cos. Okay, so we can go back to sine and cosine and see if we have any cancellation or any manipulation we can do. All right, so if I just go back to, in fact, I'll just cordon that off. So for the next step, if I replace the cosec and the cot using that third letter rule, okay, so I know cosec is 1 over sine, so I can put that in the numerator. Let's do that. So that's going to equal 1 over sine squared theta. That's the numerator, okay. Over, so just to make that clear, so this part has been substituted, or has been used as a substitution for this. And then in the denominator, I'm not going to use the 1 over tan. I'm going to use the reciprocal of sine over cos, because we want to use those basic building blocks, don't we? Tan has basic building blocks of sine over cos, so I might as well use them. And cot is the reciprocal. So in the denominator, I'm going to get cos squared theta. These are squared, remember, over sine squared theta. Okay, and just to show you the substitution that I made there, all of this, and we've used it previously, is a substitution for this. Okay, now I'm just going to draw an arrow. I'm running out of space on here, so I'm just going to draw an arrow over to this side so we can do our next step. Now you'll notice we have sine squared in the denominator of both of these. Now it depends how you want to interpret this. I like to clear the fractions by multiplying the numerator of the larger fraction containing the smaller fractions. So I like to multiply both the numerator and the denominator by the denominator of the fraction inside the fraction, if that makes sense. That way I can clear the sine squared. Also, you can think of it as if I've got a fraction divided by another fraction, you can use the switch and flip. And in fact, I think I'm going to do that. So we have 1 over sine squared theta divided by cos squared theta over sine squared theta. Okay, and so I don't waste space, if we just use the switch and flip rule, so we can change this to a multiplication provided this fraction is flipped over. Okay, so let's do that. So I'm going to erase this and I'm going to put in that extra step, just sort of overlay it. So I'm going to multiply by sine squared theta over cos squared by flipping. And this is the step, okay? So this is the powerful step. We've got a cancellation here with sine squared. So we are simply left with 1 over cos squared theta. And you'll know from the third letter rule that 1 over cos squared is, of course, sec, okay? Or sec squared. So there's our answer. So this is equal to sec squared theta, which is, of course, r squared as required. Now, there's more than one way of attempting that question. If you prefer, if we go back to the original thing, you could actually write everything in terms of sine and cosine from the outset. So if you look at P is, of course, 2 over sine theta. Okay, so that's the basic building block. So you'll have sine theta in the denominator from the outset, and then you can clear the fraction from there. But that's completely up to you. So you could use the sine theta from the outset. So maybe try this example using a couple of different techniques and see if you still get the same result, which you should do. All right, so we've seen how these new identities can be used to solve some angle reasoning problems with cast, some proofs. And now we're going to have a look at a trigonometric equation similar to those that you met in year 1, where you were using sine and cosine and tan. This time we're using our new reciprocal identities, cot, cosec, and sec. And notice, of course, before we start, we've got an equation that we need to solve in the interval between 0 and 2 pi. So this is clearly in radians. So you might want to set your calculator to radians before we begin. Before we get on to any of that, we need to look at the equation that we've been given and decide what needs to be done. Well, if we look at that, we've got a squared term, which is the first term of this equation here. So it's a squared term. We have a non-squared term and we have a constant. Now, if you have a squared term and a non-squared term, this is clearly a quadratic. Okay, and there's some kind of substitution that can be done to make the quadratic a little easier to manage. Our initial problem, though, is the fact that we have cosec and cot in the same equation here and here. So that's a problem. So we need some way of getting the variable, well, it's not the variable, but we need to get the trig ratio the same before we can do any kind of processing of quadratics. Now, when we were doing this in year one, there is a basic approach to this. If you look at the non-squared term here, this is telling us how to start the problem. Okay, so the clues are there if you know how to read them. So this is telling us to get this quadratic in terms of cosec theta. That's what that's telling you. It's the non-squared term that you have to use. So if it was the other way around, if it was 2 cosec squared theta subtract 7 cot theta equals 2, you would want to get everything in terms of cot theta, okay? Because that would be the non-squared term. So whatever the non-squared term is, that's the ratio you're going to be using. The ratio, I mean the trig ratio. So it could be sec, cosec, cot, sine, cos, or tan. So in this instance, it's cosec. Now, we need to think, if I want to convert between cosec and cot, which is what I'm going to be doing, or I'm converting cot to cosec, there must be an identity that links the two, and indeed there is. So let's make a note. We're going to be needing this. So we're going to note the identity. So we should be familiar now that cosec squared theta is identical to 1 plus cot squared theta. That's from earlier, the result earlier. Okay, so let's begin. So this is where you'll get some credit. So for the first step, we're going to start and we're going to write 2. Now, instead of writing cot squared now, we can now replace it with an expression in terms of cosec. Okay, so let's just have a look at how this will pan out. Well, if it's cot squared, notice from the identity that if I subtract 1 from both sides, which we've done previously, I get the cot squared isolated as the subject. So that's good. So I'm going to replace the cot squared with cosec squared subtract 1. Notice I'm not saying cosec squared theta. I tend to drop that, but that's what I mean. Okay, then we're going to subtract 7 lots of cosec theta, and that is apparently equal to 2, and we'll worry about the interval later. Let's expand, collect like terms. Okay, so therefore we have 2 cosec squared theta, subtract 2, multiplying the entire bracket by 2. As you can see, please don't forget that. So it's 2 multiplying everything inside the bracket. And then we write the rest of it. So that's going to be subtract 7 cosec theta. And I'm going to subtract 2 from both sides of the equation. So I'm going to subtract 2, and that's going to equal 0. Okay, so we want a quadratic equation, don't we? Right, let's collect like terms, continue to do that. So we're going to have 2 lots of cosec squared theta, subtract 7 cosec theta, subtract 4 is equal to 0. Now, usually, if this is in an exam situation or in a question in a textbook, these usually factorize. You'd be unlucky to get one that doesn't factorize. So assume factorization here, and you can go straight ahead and factorize it as it is. If you're not comfortable with that, it's a good idea to perhaps make a substitution, which I'll do here. So we're going to say let big X equal cosec theta, okay? So that means that my equation is going to look like this. So we're going to have 2 multiplied by big X squared, okay? Subtract 7 multiplying big X, and then subtract 4 is equal to 0. Okay, and factorization. So up to you how you do this. I've always done it this way. Okay, so we need -7. So I think a -4 here will do nicely, and a +1 in there. That will give me the -7. Okay, we can solve this equation for X now. Now, so we're going to get X would equal -1/2, or X would equal 4. Okay, so we've solved for X. Now we make that substitution again. So we now know that cosec theta is equal to -1/2, or cosec theta is equal to 4. Okay. Right. Okay. Now, because we're going to be solving in an interval, we don't want to be using cosec, sec, or cot for this. Let's use our original trig function. So we'll use that 3rd letter rule. Just remember, if you're getting used to this, that's good. This 3rd letter is, of course, S. This is a sine reciprocal. So we'll write it as that. So this is going to be 1 over sine theta is equal to -1/2. And the other option, same thing again, 1 over sine theta would be equal to 4. Now, just to finish this off, we just reciprocate that, and we've got 2 solutions for sine theta. So therefore, sine theta will equal the reciprocal of -1/2, which is, of course, -2, or sine theta is equal to 1/4. Right. And we'll just stare at these for a second. You'll be more familiar with sine than you will cosec. And if you stare at those answers, you'll see that one of those is not valid. It has no real solutions whatsoever. Okay, this one, you remember the range of sine is between -1 and 1 inclusive. That's outside that range, so there's no real solutions. So we can ignore this completely. And the only one we need to focus on is this one. Okay, so after all that work with our new trigonometric identities and our quadratics and all the new stuff we've learnt, we now have to solve the equation sine theta equals 1/4 in the interval that was stated at the beginning, okay, which was something we've done fairly recently. Okay, so that will be the next stage of the question. All right, so let's do that. Now, this is going to be a cast diagram situation, isn't it? So we'll just review what we've got. We've got a very simple equation. There's no adjustment to make to the interval. So we can go straight for the principal angle now. So I'm just going to state the principal angle. So we do the inverse sine of 1/4. No negative sign to worry about there. Okay, so this is where we're going to use the class whiz. Okay, so get the class whiz. Now, we need this in radians, but I'm going to do this in degrees and convert to radians at the end. So just notice on here, my calculator, it's deliberate. Okay, I've got it set on degrees there. I like using degrees. I'm more familiar with it. So I'm just going to stick with that and remember to convert to radians at the end. Okay, so if we do the inverse sine of 1/4, so that's shift and sine, and I'll just put in 0.25, which is the same thing. Okay, and what do we get? Okay, so we get 14.47, 14.48 to 2 decimal places. So let's write that on there. Let's get rid of that. So that's 14.48. Two decimal places. Okay. And now we have our principal angle. I'll just make an adjustment to the interval up here as well. So that's going to be between 0 and 360 degrees, as I'm sure you're familiar with now with 2 pi radians. Get the cast diagram going, and we can get all the solutions. So we've got C, A, S, and T. Okay, and the value 1/4. If we just look down here, again, this value was positive. It's a positive value. So we put our principal angle here in the quadrant where sine is positive. So sine is positive in S and A. That's all there is to it. So let's add our angle. So we're going to have 14.48 degrees there, and 14.48 degrees there. Okay, and we just read off the answers. So theta is going to equal 14.48 degrees, and then simply subtract 14.48 from 180, which I'll do. So that's 165.52. Okay, we only need to go around once. Okay, once in that direction. Okay, so those are our answers. Now, what we have to do now is make sure we've got them in the right units. So we need to convert to radians. So to do that, I'm just going to go down here so I've got a bit more space. So my answer theta, I simply have to multiply each of these answers by pi over 180. Okay. So just to finish off, so we've got 14.48. Okay, and then pi over 180, and that will be in radians. Okay, we'll work that out in a second. And then the second angle would be 165.52. So they're not going to be nice answers. Okay, multiplied by pi over 180. Okay, so just convert those into radians and we're finished, and we'll give our answers to 3 sig figs. I think we'll do 14.48 multiplied by pi. So I'll do shift and the button in the center at the bottom, which has both a pi and e function, in fact, and then divide that by 180. Okay, and that gives us our first angle, which is going to be to 3 significant figures, 0.253. So I'll write that in. Okay, that's radians, of course. And our second answer, go back to the calculator, just erase that. So we've got 165.52, multiply that by pi, and then divide by 180. Okay, and we get 2.89. All right, so if you have time, of course, and this is an exam question, you can check whether these answers do in fact work. Okay, you need to set your calculator to radians. But I think in principle that concludes it. So you'll notice as well how we've again, we're adding new layers of knowledge, okay? Very subtle, we're just building gradually. And the questions seem to take just that little bit longer, don't they? Okay, because we're adding this new layer, okay? But we're still revising those key skills that you learned back in year 1, and we'll continue to practice throughout year 2. So I hope that was clear, and that concludes the lesson.